Okay, so think back to chapter 2. This dealt with a lot of patterns, some hints if you're looking for those patterns. See if you can add the same thing to get the next number, if you can use subtraction, multiplication, division. Their term numbers are perfect squares. Like 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25. See if you can use these perfect squares. Otherwise, if there's fractions, think about rewriting them with common denominators. Or find patterns for the numerators and denominators separately. Treat the tops and bottoms separately. If the pattern looks like it's alternating, you could even find a pattern for the odd and the even terms separately. So we use that letter N, which stands for the term number. We always want to start with N equals 1 for the sequence. And you're always going to start the term row with 1. So when I want to start filling in this table, my first term is 7. My second term is 2, third term is -3, fourth term is -8, fifth term is -13, and my sixth term is -18. So that's as far as we can fill in the table. We want to find the common difference. So each time for our y values, we were subtracting 5. Okay, so that's our common difference. We want to circle a term and its value. Let's say I want to circle the term 1, 7. Now we're going to plug this into the equation. So normally, if it has a common difference, this will be a line, y equals mx plus b. This -5 is our slope. Okay, we circled 1 and 7. We can plug them in. So 1 is x, 7 is y. So this equals -5 plus b. When I add 5 to the other side, I'll just move it down here. 12 is b. So your equation is really y equals -5x plus 12. In this case, though, we were using n values, so you could just say -5n plus 12 if you were looking for the nth term. Okay. So functions are linear when they have the same common difference. That means that they have the same slope. If you were to graph it, it'd be linear. Okay, so sometimes you're going to have a table that increases or decreases by the same number sometimes. Other times you might have a table that does not increase or decrease by the same number. These are handshake problems. So if you want to count the total number of handshakes that happen at a party, when you had n people, you have to shake hands with everybody but yourself, and then you're going to divide that by 2. So a lot of times if it's not linear, try to think of using these types of handshake problems. Maybe it's asking for like a round robin tournament. Or maybe it's talking about conversations. Okay, a lot of times those are the same as handshake problems. Then in this diagram below, if we have a line that intersects 2 or more other lines in a plane, this is called our transversal. So there it is in blue. So in this diagram, that transversal creates 8 different angles. So we have our alternate interior angles. They're alternating sides of the transversal. They're both on the inside, so one pair there would be angle 3 and angle 6. Another pair would be angle 5 and angle 4. Alternate exterior angles. Now they're on the outside, alternating between the left and the right of the transversal, so that'd be angle 1 and angle 8. Same with angle 2 on the right, angle 7 on the left. And corresponding angles, those are in the same matching location. So if I look at this top line, angle 1 really is to the left of the transversal and above its line. Same with angle 5. They are corresponding. They're in the same matching location. If I look at angle 2, it's to the right of the transversal above the line. Same with angle 6. Angle 3 is to the left of the transversal below its line. Same with angle 7. And lastly, angle 4, angle 4 is to the right of the blue transversal below its line. Same with angle 8. Oops. If two parallel lines are cut by a transversal, then your alternate interior angles are congruent. Your alternate exterior angles, I'm just abbreviating those, are congruent. And your corresponding angles are congruent. So if you want to put a sketch of that, if you knew that these lines were parallel, they either told you or there were some sort of markings. Here's my transversal in blue. Then those four angles would be congruent. And those four angles would be congruent. And on the very bottom of the page, we have one of those billiards pool table problems. So this is when you would need to use your protractor. Alright, so if the ball is not hitting the wall, kind of extend it towards the wall. Then you're going to take your protractor and we need to measure angle 1 there. So if I look at my protractor, I can see that incoming angle is about 45 degrees. Okay, so that means my outgoing angles, starting from the 0 going up, needs to be 45 degrees also. So angle 1 was my incoming. That angle is 45 degrees. When I use my straight edge and connect this back, this angle here is also 45 degrees. Those angles are congruent. There's my outgoing. I could bounce this off another wall. So I continue that until it hits the wall. Now this angle here is my new incoming angle. Now I'm going to have to spin the protractor so I can measure what that incoming angle is. It's 50 degrees. I can even mark that without even moving my protractor. Then using a straight edge, I can connect that back. So there's my incoming. What did I say? It was 50 degrees. So that means my outgoing is 50 degrees there also. Your incoming angle is congruent to your outgoing angle. And that's all we have for your chapter 2 review.